This meeting is being recorded.
Jeez. Is there? Somebody renamed themselves?
Yeah, that's me. I missed lecture this morning. I came to this one.
Okay, fine. Where was I? This one. This one. Here we go. Okay. Alright, we're good to go. So crowded in here today. Good afternoon, everyone. Before we start, are there any questions that I can answer? About topics, the exam tonight, or anything? Wow, no questions. Okay, so just a reminder, exam is tonight at 6 p.m. Will be similar to the last time, except for all the screw up at the beginning when it failed on you. So we will go directly with hand-ins. Basically, the descriptions of the problems will be available there. There will be also a starter file, which will be basically just a record file with sections in it that you are supposed to fill in. Please don't move the sections around. What else? As previously, you are allowed to have one printed sheet of notes or written sheet of notes, and are not supposed to use any other material. Nothing online, nothing in print. So there's that. What else? If there will be any technical difficulties, we will be monitoring Piazza for private posts if there are some issues, but in general the policy is not to answer topic questions on the exam. So hopefully, multiple people have looked at the exam, and it should be pretty self-explanatory. Provided that you studied for it, you should be good to go and should be able to tackle all of the problems. Okay, so if there aren't any other questions, I want to crack on with the lecture today. So I want to do one more example of parallel traversal of complex data before we move on to yet another type of a data structure. So what we've been doing last week, I think the last two lectures, if I remember correctly, we've been looking at parallel traversal of complex data, so how to write functions that take more than one complex input and might want to process them in parallel. So the last example that we will look at is an example of family trees, which should be relatively easy to understand after a similar example on one of the last assignments. A family tree is either a none, which was, I think, called unknown in the assignment. Then we have a person with a name and two ancestors, which we call mother and father. We also define another data structure, and that is called an ancestor path. Okay. An ancestor path is just a list of ancestors, where an ancestor is either a mother or a father. So basically, it's a way of specifying where to go in the family tree, and we will see examples of that. So hopefully, that will clarify that. Here we have a few examples, basically building one major example in here. Also visualize it. The root of the tree is Alice with the mother and the father. The father is Bob, who has unknown ancestors. The mother is Claire, who has a mother Sarah and a father Dave. Dave has unknown ancestors. Sarah has an unknown mother but a known father, Zach, who again has unknown ancestors. So a pretty typical example of a tree, something that we've seen in class and on assignments. Okay, so given a data structure like this, or two data structures like this, right, the family tree and the ancestor path, we want to design a function which, given a family tree and an ancestor path, determines the name of the ancestor designated by the path. Okay, so let me give the signature and give a few examples which will illustrate what we mean by the ancestor path there. So given a family tree and an ancestor path, determine the name of the designated ancestor. Bless you. Since there might not be an ancestor in the family tree that corresponds to the ancestor tree, we will use the maybe string data type that we used a few times, where we either return false or we have a string. Okay, let's do a few examples. So we'll use the example tree over there, and if my ancestor path is, for example, mother, then the mother, meaning I'm looking for the mother of the root of the tree, which means that I start with Alice, go to the mother of Alice, which is Claire, then go to the mother of Claire, which is Sarah, and I return Sarah as the result. Yes. If on the other hand I go to mother, father, then I'm expecting Dave. Father of Alice is Bob. In here, let's get to Zach, which would be Alice's mother, then the mother of Alice's mother, and finally the father of the mother of Alice's mother. So mother, father. Should get us Zach back. Let's do some negative examples. In particular, if I have an empty tree, then no matter what I select from there, I should get a false, because there's nothing sensible to return. If I have a family tree that contains something and I go down the path that doesn't contain any ancestors, should get a false. And finally, oh, here's one more positive example. So if I have an empty ancestor tree, ancestor path, then I just want to return the root of the tree, so the immediate one. Okay, so it's just a you can think of an ancestor path as basically as a way of querying a family tree. Okay. If you're familiar with jQuery, this is a simplified version of that. Okay, so we have the signature, we have a few examples, we have the data structure that we want to work with. Since we are working with two complex data inputs, I will start by writing out the template for this one, and that is ftap temple ftap k. How many cases will be in the cross product template for this one? We're combining all of them. Charlie? 4 cases. We have 2 cases in the family tree, so either none or make person. And we have 2 cases in the ancestor path, which is a list, meaning we have empty and we have cons. So let me write those out. 4 cases in here. So we either have a symbol meaning none and an empty ancestor path, or we have a empty tree and a non-empty ancestor path, or we have a non-empty tree, so we have a person in our family tree and an empty ancestor path, or we have a non-empty tree, we have a person and a non-empty ancestor path. Okay, so it's usually trying to combine all the possible combinations that might arise. When we have an empty family tree and an empty ancestor path, there's no information really to work with. None of these base cases contain any fields, so we can leave the 3 dots be. If we have an empty family tree but we have a non-empty ancestor path, that means the list template would give us the first of the ancestor path, and also a recursive call to the list template, which in the cross product template translates to a recursive call to the cross product template, where we use the rest of the ancestor path. Okay. Now, in this case, we have a name for a person, and then we have a mother and father. Right? If we would write out the family tree template for the case where we have a person here, we would have an arbitrary operation with the person name, but we will have recursive calls using the mother and the father. So again, in the cross product template, translates to our recursive calls to our cross product template. And finally, the final case, when we have a non-empty tree and a non-empty ancestor path, we have the most information that we can process. We have the person's name. We have the first of the ancestor path. We have a recursive call to using the person's mother and the rest of the ancestor path, as well as a recursive call using the person's father and the rest of the ancestor path. Okay. So again, just combining all the cases and then recombining the two templates in the bodies, right? Considering what information we have available. Any questions about this template? Yeah, Charlie?
So just to make sure, the symbol cases are for when the family tree has reached none or none, right?
Yeah. So because we declare that the empty case is just a symbol and there's only one symbol case, we assume that a valid family tree is given. Okay?
Okay, so in our content, in the second case, we have, okay, so we've reached a none, but we still have items in the ancestor path.
Uh-huh.
Do we need to, like, iterate through more there? Because if we have a none, we know that there aren't more ancestors above.
Well, it depends on what function we are writing, right? Right now we are writing a name of, and it might make sense or might not make sense. But in general, you might want to still recur on the few remaining things, depending on what your processing is. There are certainly cases where this might be a useful thing. Okay. Hey. So let's do the function itself. And let me copy the template. Let's also make the examples a little. Okay, so if we have an empty family tree and an empty ancestor path, what shall we return? Charlie? False. Nothing to return there. No ancestor in the ancestor path. No person in the family tree. If we have an empty family tree, but we do have some item in the ancestor path, what can we return in this case? So the ancestor path is still indicating that we want to keep looking inside of the tree, but there is nothing in the tree. We haven't reached the end of the ancestor path, but also we have nowhere to go. So this is the second case where we will return false. Okay. So now we have two slightly more interesting cases. If our ancestor path is empty, but we do have a person in the family tree. Josh? We just return the person's name. That's an example of this is exactly this one, right? So if we reach the end of the ancestor path, we simply return the root of the tree, if there is one. So we can get rid of the recursive calls and simply return the person's name. Okay, last case. If we haven't reached the end of the ancestor path and we still have a non-empty family tree, what do we do? Charlie?
So we want to find out either father or mother.
Right.
We need it basically to tell which one it is.
Mm-hmm.
We can also do it with a not.
Yep. But let's say.
Compare that to either one arbitrarily.
Yep.
And then we recur on where it says FTAP template, we just rename them.
Exactly. And we don't need this person's name, so we can simply delete that part. If we so so in the last case, when we haven't reached the end of the path and we have a person, we need to check which direction we need to go. So we look whether the first of the ancestor path, meaning where do we go next, basically, is the mother side or the father side. If it's the mother side, we go process the rest of the ancestor path going down mother side. Otherwise, if it's not mother side, we assume it's father side and go in the other direction. Let me check if I wrote this correctly. And we did. We didn't hit one case, which was if we have both an empty tree and an empty ancestor path, which we can fix. And we're good. Okay. Any questions? Does this function make sense? Of course, now that we wrote it, we can go in and simplify, right? Because we can notice that whenever we have an empty family tree, we return false, so we can simplify these two cases to simply be if the family tree is a symbol, so meaning it's an empty family tree, then we simply return false. Otherwise, we must be in the person case, so we can delete the person check from both of these and simply distinguish whether we have an empty ancestor path or we still have something to process. Okay, but you can do this on your own if you want to. Okay, so processing two complex inputs, especially if there's not too many cases, it might help to write out the cross template and making sure that you hit all the cases. As you get more experience, you will kind of do it automatically. But it's still good to do this kind of cross product con check, because that ensures that you are hitting all the cases. It also helps you to write an exhaustive, relatively exhaustive test suite or kind of a suite of examples, and you can simplify from there. Okay, so that's for two complex inputs. So I want to talk about another kind of data structure today. Again, like we built up from the beginning of this course, starting with atomic data, then adding union data and enumerations, adding structured data, right, with using structs containing multiple fields. Then we went from structured union and enumerative data to data with infinitely many possibilities by introducing list-like data or self-referential data. So having data definitions where at least one case has a self-reference to the data type itself, which ensures that we have infinitely many possible values. Then we recognize that there is nothing really special about just having one self-reference case and we went on from lists to trees, which have a branching structure, right? We first had only 2 branches, and then we generalized to arbitrarily branching trees from 0 to as any number you might want to pick. But as you might expect, these data structures are not suitable to represent any kind of data that we might want. And here's an example. So let's say that I'm writing an application for kind of figuring out what flights do I need to take to get from one place to another, right? So I want to fly from, let's say, from Boston to Denver, and I want to check, okay, what are my possibilities, right? Let's say that I want to fly from Boston to Denver and back. So for my application to be able to look this up, it needs some sort of representation of the flight connections, right, between different cities. So there might be a direct flight from Boston to Denver and from Denver to Boston. There might be another option where we, I don't know, fly through whatever, Kansas City, right? So we take a flight from Boston to Kansas City and then from Kansas City to Denver, right? So as an example, my representation will need to be able to represent something like this. So I have a flight from Boston to Denver, direct one. Then I said there's a possibility that I might catch a flight to Kansas City, and from there to Denver. And I also said it's possible to take a flight back. Okay. Now my question is this a tree data structure? No. If it was the case that I can only take one direction and there's only one way that I can reach any destination, right? So if there wasn't any way of going back here and there wasn't any connection from Kansas to Denver, then this would be a perfect tree structure, right? Because at each point I can only take one direction, there's no way of going back, etc. So it's not a tree. It's also definitely not a list, because we might have multiple branches at some places, not on this one, right? No, actually, from Boston we can go both to Denver and Kansas City. So it's not a list-like data structure. It's not a tree data structure. So how could we represent this? Josh? It's a graph, exactly. So graph is a further generalization of trees, right? In the sense that everything that's a tree is also a graph, but not everything that's a graph is also a tree. A graph is a data structure which allows connections going in both directions, and moreover, multiple ways of reaching the same connection. Okay, so over here, we not only have this path to Denver, but there's also this cycle to, or this other way to Denver. So where we would start as a tree, we would need to kind of have a shortcut somewhere there, and there's also a connection going there and back. Now let me just do a little bit of terminology here. So these pieces, just like with trees, I think, if I remember correctly, we call them nodes, right? So these are the different pieces that are interconnected. In our example, it's airports. The connections between nodes, just say nodes. Connections between nodes are what is called edges. Okay. Just as a aside, sometimes, or like some literature also calls nodes vertices. So it's a vertex connected by edges. Connected by edges. Now these edges, depending on the type of graph, can have a direction, but also don't need to have a direction. And in this case, I chose to use a direction. So for example, in my graph, there is no way of going from Denver back to Kansas City, which might not make sense, but it's just a representation. So the direction is significant here, right? Because I can go from Boston to Kansas City to Denver. I can go from Denver to Boston, but I cannot go back there. So direction matters in there. I can also have undirected graphs. Okay, so if I chose to say, okay, direction doesn't matter because there's this assumption that if I can fly to one airport, I can also fly back, then I could omit the direction and I could go either way. Another example is, for example, social media relationships, right? To be a friend with somebody on Facebook, they have to friend you back, right? So it's bidirectional in any case. So the direction doesn't really matter. If I'm somebody's friend, they're my friends. On the other hand, if we have, so that can be represented easily as an undirected graph. If we have a Twitter, for example, and somebody follows me, I don't have to follow them back for them to be a follower of me. So that is very much directional, right? I can choose to follow them back, in which case there will be an edge between me and them and me, but it's not necessary. That can be very much directional. Another directional kind of example would be if I like somebody, doesn't mean they have to like me back, right? So it can be very much directional. If I'm related to somebody, they also need to be related to me. So that's undirectional. Okay, so those are examples there. And a third piece of terminology that we will use today or next time, depending on how far we got, is whether graphs contain cycles or not. Okay, so this particular graph contains a cycle because I can go from Boston to Kansas to Denver to Boston to Kansas to Denver, etc. So we have a cycle there. If I broke this cycle by removing one of the directions, there is no longer a cycle, right? Every road leads to Denver, but there's nothing going out of Denver. So, and acyclic. So that's just a little bit of terminology associated with graphs. There's many more different types. And as I said, trees happen to be just a special case of graphs. Okay, so that was an airport example. The actual example that we will work with today is what we call a caller graph or call graph. Okay. This slightly silly example is basically representing a graph of people who called who in for example, a group of friends, right? The way we can represent the graph is by listing all the nodes in the graph, and for each node we list its name and also the list of the nodes that it's connected to, right? In the direction that they are connected to. Okay, we take a name just being a symbol. In this case could be a string, but symbols are kind of useful here. And a graph is, as I said, just a list of nodes. Each node has its name and a list of connections from the node to the other nodes. Okay. Any questions about this data so far? Okay. Oh, we also add a little constraint here on this data structure, assuming that all names that are mentioned somewhere do have a node. So in particular, this means if a name appears in one of these lists, it also appears as a node on its own. Okay, that's the only way we can have a well-formed graph. Here are some examples. The first example, we have the nodes Amy, Billy, Claire, Dan, and Eli, right? And we have the following connections. So Amy called Billy and Claire, Billy called Dan, Claire called nobody, Dan called Eli, and Eli called Claire. Let me visualize this. So we said we have Amy, we have Billy and Dan and Eli, and we have Claire, and we have the following connections, right? So Amy called Billy and Claire, then Billy called Dan, and then called Eli, and finally Eli called Claire. Okay, so that's a representation of this graph. One special node that didn't call anybody, so there are no edges leading out of it. So that's a good graph because every name that appears here, right? Billy, Claire, they do have a node. Dan has a node. Eli has a node. Claire has a node, which we already checked, right? The empty list, there's nothing to check. So this is what we would call a well-formed graph. Here's a counter example, right? It's almost the same graph, but now Claire is calling Amal, and we have a problem because Amal doesn't appear in the list of the nodes. Okay, so this is not a well-formed graph. This is saying, okay, they're calling somebody that's outside of the group of friends. It's not a well-formed graph. And here's another graph, right? Amy calling Billy and Claire as before, Billy calling Dan, Claire calling Eli, then calling Amy and Claire, Eli calling Claire. And in particular, if you notice, Claire calling Eli, Eli calling Claire, we have a cycle here. Okay, so that's another example. Okay. Any questions about these graphs, this graph representation? Okay. So the first function that I actually want to write is a function which will check whether a given graph is a good graph, meaning whether we have a graph where all the nodes, all the callees, so any node that appears in the list of callees in the node appears also as a node in the graph. So does every callee in the graph? How could we go about this? Any ideas? So I think the first thing that I would like to do is for me to be able to check whether every callee in the graph also appears as a node in the graph, it would be quite nice to have a list of nodes in the graph, a list of names, right, that appear as nodes. So let me do that. All names. Okay. Since a graph is a list of nodes, we do have a function how to get a name of a node. The simple way of how we can get all the names is simply to map node name over the given graph, right? So we have that. Okay, now that I have all the names, what do I need to do? Josh? In something like this? Sorry? Yeah. So what we need to do is to, for each node in the graph, right, where the graph is a list of nodes. So basically, what we want to do is to do an nmap, because we are checking whether for each node of the graph do all the callees appear in all names. Right? Did I have the, yes, callees. Where was I? Here. Okay. So this sounds like a lambda for all nodes in the graph. We need to do something with the of the node. And with all names. What it sounds to me is like another nmap, right? Because for each node, for each callee in the node callees, does the callee appear in all names? So what we can do here is write it as another nmap for all callees in the list of callees of the node is the, and what we can use here, there's a function called member. Simply check if an element appears in the list. No, of course not. Thank you. Actually, I cannot have parentheses around all names. Okay. For each node, right, and for each callee of the collection of callees of a node, is the callee a member of all names? And it would probably help to break this down a little bit. We can say we can have a function that does the inner lambda. So callee, yes, and let's say or our nodes, for example, and we need the list of callees, and we can simply copy the definition and just use k, and here we just say okay. So for each node, are all the nodes callees nodes themselves? If yes, then we should be okay. And let me just check on the few examples that I have here. Of course, let me move the layout around a little bit. Now it should be good. I didn't close my lambda. Anything else? And we're good. Does it make sense? Any questions? We're good. Okay, so now we can check whether a graph is good and valid. So the next thing that I might want to do, similarly to my previous kind of example with my airport connections, is to find out whether there's a path between one node and another node. Okay, so in particular, the example would be, let's say that I'm given this graph and I want to find out, is there a path between Amy and Eli, for example, right? For that to check, I need to check whether any of the nodes that Amy is connected to has a path to Eli, right? So I can go to Claire. With Claire, I will find out that her callee list is empty, so I'm done there. But maybe Billy has a path to Eli, right? To check whether Billy has a path to Eli, I have to check whether Billy's callees have a path to Eli. And then it turns out that Dan has a direct connection to Eli, so there is a path, right? So in particular, this shows that we have 2 or 3 options, right? Either the list of the path is broken somewhere, so we cannot get to the person, right? Like with Claire, we can get to Claire, but then we cannot get to Eli. Or we can get to the person if they are directly adjacent, so there's a path between Dan and Eli because Eli is a callee of Dan. Or there's a path from Amy to Eli because Amy has a callee that has a path to Eli, right? And that callee has a path has a callee that has a path to Eli, etc. So that's what we are trying to do. So let's start with fleshing this function out. So, as I said, trying to write a function, given a graph, 2 names, returns true if there is a path from one name to the other. We make an assumption that the given node actually appears in the graph so that we don't have to we don't have to check that, so it's always there, and also we actually don't need to make the assumption about B. Here are some examples that we want to check, and one devious example. So, how should we go about this? Kind of laid it out by going through the examples. What's the easiest case that that would mean that there's a path from A to B? Yes?
Is that where we are is the thing we're looking for?
Yes. So that would be one, but we can also simplify it. So there's not necessarily in a graph, it's actually not necessarily true that there is a path from the node to itself. So we don't have that as a base case, but our base case is actually, does the case B is A's Collie, right? So we either have that B is a member of node Collie A, there is a slight problem here immediately.
Isn't B also a node?
Sorry?
Would you have to like make sure that it's like node name of B?
Yeah, exactly. So the types don't fit here, right? Because node Collie is defined on a node, whereas A is a name. So instead of just getting the name, I need to have a way of retrieving a node based on the name. Or actually, I can just simply write myself a little function that returns the collies of a node in graph G. So let me just do that. So I want a helper of which takes a graph and a name and returns a node. Actually, a list of names. We have graph, we have name, and the list of collies of the node with name and in graph G. Assume A appears in or and appears in G exactly once. Any suggestions how we might do this very quickly, very simply? Using this as assumption. Charlie?
So, can we match node names to the list of nodes and colleagues and
Map. Sorry?
I mean, where does G fit into it? Because what I'm saying is like, just match the function that gets the name to the list of nodes.
So what I want from here is, given a graph, right, where we have a list of nodes with names, and given a name, I want the list of collies associated with that name in the graph. All right, so just to recap here. A graph is a list of nodes. Each node has a name, and has a list of callees. Right? And I want the function, because what I really want is, given a name, give me the list of callees. So basically a lookup for that. Okay. Yeah? Uh-huh. Yeah, perfect. If we use this assumption, right, there's exactly one node with the name, then filtering it out based on the name should give us a list of 1. Then we can just take the first of the list. So what I want here is to get a node and then check whether the node name is the same as the name that we're looking for. This should return a list of 1. So what we can do to get the node from the list is to simply take the first element. Once we have the first element, what we want from that element is really the callees. So what we do is just do node callees on that one. Okay. Just because we have this assumption, we can use this little filter approach. Okay, so we can get a list of callees. Now we can check whether B is included in the list of callees, in which case we have a path, right? So if this is not true, if this is, sorry about that, this is not true, right? What's the alternative? Yeah? Exactly, perfect. So either it's an immediate callee of the node, right, that we are looking for, or we simply map the list of callees. So and we check whether for each callee is there a path in graph G between the callee and B, and we map this over of GA, which is the same thing, right? Very good suggestion. Yeah? Here? So we established that B is not an immediate callee of the node A, right? So what we want to do instead is to check each callee of node A, whether any of those callees has a path to the node B. So callees is a list of names, right? So I take each name from the list of callees and check whether there's a path between that callee and B. Right? And it goes through the same process, looks up the callees of that callee, list of callees of that callee, and again checks whether either they are immediately related or there is a path from there. Okay. Now I want to save a little bit of work here, which is why we introduce local, or one of the reasons why we introduce local. And I want to say that save the result of A, callees of A as a variable. this is also Collies A. So again, just to repeat what we are doing here, there is a path from A to B, either if B is a Collie of A, right? So there is an immediate relationship, or if at least one of the Collies of A has a path to B. Okay, that's the recursive thing. Now, does this, does this example cover, does this function cover this example, right? Where Claire didn't have any Collies, which was the case where there is no. I know, yes, we'll get to that. Does it take care of this case? Yeah? Yeah, so B then is definitely not a member of the Collie, so this will return false, but we still have an OR, right? And then we have an OR map, right? But an OR map with an empty list. What is the base case of OR map? Is it? False, right? So if the list is empty, it will return false, and that will take care of. So we don't need to kind of have a special case for the case where the list of Collies is empty. Okay, so I think some of you might have noticed that I have my commented example here. Let's first try and run this. Just let's check how many typos I made along the way. Some. Okay, so this works, but as Peter online pointed out, what happens if we have a cycle in our graph? All right, so in the graph C where we want to check whether Amy is calling Eli, we have a cycle there, right? Because I think Amy called Claire, Claire called Eli. Eventually my program will run out of memory. So this won't work. It's a simple enough function, but it won't work for every graph. What is the problem here? Charlie?
So we keep searching down basically.
Uh-huh.
We hit a cycle, we say add, like look through all of the colleagues, and then we get to the other part of the cycle and we look through all the colleagues again and we keep going around in this circle forever.
Exactly. So our problem here is that to check whether Amy has a path to Eli, we need to check whether Billy and Claire have a path to Eli. So we check Billy, right? Then and Claire, right? First Billy will get processed. So Billy has a path to Dan, which is good. So we need to check Dan. Dan has a path to Amy, right? So, okay, now we need to check if Amy has a path to Eli, and we are back in the same situation. We check if Amy has a path to Eli, therefore we need to check if Billy has a path, etc., and we kind of end up in a cycle. So we don't have time to actually go through the Brandon computer explode. Some of them might. So we don't have time to go through the whole solution, but what do you think would be a fix for this? Josh? So if we find an A, so somewhere in this OR, if we find in here, if A itself, if we have a path to A from A, Charlie?
So what we need is some way to keep track of where we've been before and exclude the places from where we look in the future.
Exactly. What we need is basically breadcrumbs, right? We need to leave some sort of like, okay, we've been here. We don't need to check this again. So there is I will include the example that actually fixes this using a list of visited nodes that we check every time we visit a node. Because once a node is visited, we already know that we check this, right? So we can stop there and move on to other ones. So we'll start with this next week. I will upload this code. This will be available to you. So just take a look at it. But basically, the idea, as Charlie pointed out, we need to keep kind of a checklist of like, okay, I've seen this, seen this, seen this. We don't need to check again to avoid going in cycles. Okay, we're out of time. Are there any questions that I can answer? All right, in that case, if there's nothing, good luck with the exam tonight. And after that, have a good break, take a good rest, and I'll see you on Monday. I'll do either in person or virtually. Okay, stay safe, travel safely if you are traveling. See you soon.